Hello everyone, so today we are going to prove that there are infinitely many prime numbers. So first let's remind the definition that a prime number is a natural number greater than 1 that is divisible only by 1 and by itself and does not have any other divisors. And the statement of the main theorem that we are going to prove that there are infinitely many prime numbers. So we will need a lemma that any natural number has a prime divisor. So notice that this lemma immediately follows from the fundamental theorem of arithmetic, which states that any natural number can be expressed as a product of prime numbers, and that this expression is unique up to the order of the prime divisors. However, we need here only the weaker statement of the lemma. Also notice that this lemma is more or less obvious, and the rough idea of the proof is to divide the number while we can, and when we can no longer divide it further, that would be the required prime divisor of the original number. The proof that I give below is a more detailed formalization of that idea. In my view, it's a technicality, and I actually encourage viewers to skip it. So for those who want to see the full proof of the lemma, here it is. So take a natural number denoted by n, and there are two cases. Either n is prime or it is not prime. So if it's prime, then n itself is its own prime divisor, and we are done. So if it's not prime, then n has a divisor denoted by d1, a divisor that is different from 1 and itself. So d1 is not equal to 1, d1 is not equal to n. Then we repeat the same argument with d1. So either d1 is prime or it has a divisor d2, which is different from 1 and itself. So and so on. So repeat the same argument for dk. Either dk is prime or it has a divisor dk plus 1, which is different from 1 and itself. So now notice that divisibility is a transitive relationship, and from this we conclude that on each step dk plus 1 is not only a divisor of the immediately preceding number in the sequence dk, but also a divisor of all numbers in the sequence from d1 to dk, and also of the original number n as well. Now we notice that the sequence d1, d2 and so on is strictly decreasing. So d1 is strictly greater than d2, which is strictly greater than d3, and so on. And from this we conclude that the process cannot continue forever, and it will finish after a finite number of steps. So it means that there exists f such that df is prime, and this df is the required prime divisor of n, and this concludes the proof of the lemma. So now let's go back to the original theorem, that there are infinitely many prime numbers. So suppose that the statement is not true. This means that there is a finite number of prime numbers, and we enumerate all of them, p1 through pn. So now we consider a number q, which is the product of these prime numbers p1 through pn, and all of this plus 1. Notice that q has the remainder 1 when divided by pi for any I. And in particular, this means that q is not divisible by any of p1 through pn. This means that q is not divisible by any of the prime numbers whatsoever, because p1 through pn, these are all the prime numbers that there are in existence. supposedly. But on the other hand, by the lemma, Q must have some prime divisor. And this is a contradiction, which concludes the proof of the theorem.